Well, good evening, everybody. This is Dean, KK4DAS. This is the regular meeting of the Vienna Wireless Society Makers Group. It's the 8th of January, 2025, and tonight we're kicking off our 2025 Makers project. We're very excited about it. We're going to be building the front end of a software-defined receiver. We're going to start from schematic, go all the way through lay out a PCB, having PCBs fabricated, and then at the end of all this, we'll have a build day. And the project that we have chosen is the front end of the software designed receiver, um, based on a transceiver that was designed by Jack Purdom and Al Oliver. What's Al's last name?
Peters?
Uh, Al Peters, called the T41. And we're not building the whole T41 transceiver. That's a much bigger project that we're going to get involved in. We're just going to do the receiver front end, a modified version of the receiver front end. And Oliver, KI3P, has been heavily involved in the T41 project, doing the circuit board layout for those things, and he's graciously volunteered to lead us through this process, which is going to take us through the first couple of the months of the year to get to conclusion. So I'm going to stop talking and let me hand it over to Oliver, KI3P. Over to you.
Thanks, Dean. As Dean introduced me, I'm Oliver KI3P. I've been licensed for a few years as a ham and joined Vienna Wireless Society last year. I have no association with the KiCad project. So this project idea came out when I joined the first makers meeting that I made, and Dean was like, "Oh, you know all about KiCad," and had some experience doing circuit board design and layout in KiCad and surface mount assembly using KiCad. These are tools and techniques that other makers would like to learn. Can we conceive of a project based around that? These two goals. One is learning the KiCad tool in particular, and the second is get more familiar with surface mount assembly and how you design, how you lay out, and how you build surface mount assembly um, uh, object. Can we come up with a project with those two goals in mind, and we came up with this the RF front end for a software defined receiver. So, like I said, I have no association with the KiCad project. I'm just an enthusiastic user of it. A fair amount of experience now with doing kind of like ham circuit board design. So, with that preamble and that scope and purpose, let me share my screen and we'll get started. So, hopefully, you all would have seen the link um, to how to download KiCad if you want to follow along at home as we go. You're welcome to. But what we're basically going to do is, starting from scratch, we are going to recreate, just move this out the way. We're going to recreate this schematic, which is as you said, it's the RF front end for a software-defined receiver, heavily based on the receiver portion of the T41 receiver. If we look at that kind of at the block diagram view, this has gone around the mailing list a few times, but if you're new to the project, it's essentially you've got RF coming in on the left, your antenna is connected, say, to this RF connector, you've got some amplification, a gain stage, a mixer to take your RF and move it down to the intermediate frequencies. This is the Taylor mixer design, where you drive your mixer with your quadrature local oscillator signals. So you've got two sine waves or square waves that are 90 degrees out of phase. You have some differential amplification, some anti-aliasing low-pass filters, and then we'll use the USB sound card in the computer to digitize these in-phase and quadrature channels, the I and the Q channels of a software-defined receiver, and then all the demodulation and turn it into audio and all that, all the digital signal processing will happen. We'll start off by using the Quisk software because it should work out of the box, but there's conversations, thoughts about maybe having a follow-on project to use new radio to actually learn a little more about the digital signal processing that goes along with this, and so we can build off this first project with future projects. And then closing the control loop, just a microcontroller, a Raspberry Pico to basically tune the LO and pick the frequency that we will tune to. So fairly simple block diagram, and the completed schematic that we will end up with will look hopefully identical to this. We're going to start off this week with schematic layout. Next time we will do we'll do the physical layout of the board, and after that, like, okay, so now you've got a board. How do you make sure you got all the right footprints, and you got all the, how do you get your bill of materials and actually get your build files, work with a board house to get the boards made and shipped to you, kind of like finishing out the full cycle, and then we'll build them. Okay, so I am going to give you a quick overview of KiCad first. So I am running Linux, but it should look identical on whatever operating system you are running. If you open up KiCad, you will have essentially this. You open KiCad, this window will open. There's a bunch of sub-tools underneath KiCad that you use. There's the schematic editor. You can edit symbols, editing PCBs, edit footprints, UGerbers, a whole bunch of useful things. The calculator tools is actually a pretty powerful capability built into KiCad that, you know, if you're trying to do transmission line design, or all like the standard tools that you might go to find a website to get, like, how wide your microstrip line should be given a particular desired impedance, via size, spacing for different current draws, all those kinds of tools are actually built into KiCad, which is a very useful thing if you're getting seriously into the more electrical engineering RF side of this. But we don't start there. What we'll start with is a blank project. So I'm just going to start a new project. I'm going to try and, if I hit the keyboard, I'll try and narrate and describe the key that I have hit, so you can understand like the workflow. How do you get started on KiCad? What are the buttons you press? How do you actually do this? But if I'm going too fast, or if I do something that you didn't understand, please raise your hand and ask a question. So I'm going to start a new project. I'm going to call it VWS Software Defined Receiver. So if I start with a blank project, all there is the schematic and the PCB. We'll start with the schematic, lay out all the electrical circuit diagram, and then generate the PCB from the schematic, and then move all the components around and stitch them together next time. So if you open the schematic in KiCad, you will have a blank sheet to draw in. The title block down in the bottom that you can edit. Yeah, I don't know what more to say about this. It's a standard CAD tool. You can click around, explore the menus if you want, and I'm going to get stuck straight into it. So we start by basically, there's many ways. These tools there are many different workflows you can go through one of these tools, but the way I'm going to do it is place all the components, put all the components, give them the right values, put them in the right place, kind of connect them all together. Then you can go back at the end and you can use kind of like bulk editing workflows to assign particular footprints. You can also do a bulk assignment of values and things like that to the components that you've laid out. This is a slightly easier way of doing it than manually double-clicking on each component after you place it and editing the footprint of each component one at a time, which is a bit tedious. So I'm going to start by placing components. I've got the schematic pulled up on a screen off to the side here, so if I'm glancing off to the side, it's to see the cheat sheet. But you go to the place menu on the top and add a symbol. So that's the place to start. A search window will come up. You can scroll through pretty tediously and look. Say I want to put the RF connector at the input. I can scroll through and try and find RF connector, which would take a while, but I know I want a an SMA input connector. So I just type SMA into the search box, and it will come up with a few possible options. That looks about right. Coaxial connector, it's just the symbol for it. It could be a BNC, SMA, SMB, a whole range of different types of coaxial connectors, but that's a good place to start. So double click on that, and away we go. Since I'm flowing from right to left, you can use these buttons over here on the top to rotate components, or I'm hitting the R key. R keyboard shortcut can also rotate components. I'm going to flip this from left to right, and we're getting started. While I'm at it, I'm going to place the ground symbol, for because the outside shield of the SMA connector is connected to ground. That is not found under the symbols menu. It's found under the power menu, because KiCad has built into it the ability to do spice simulations. Like, you can build your schematic in the schematic view and then run a spice simulation, and you might use LT spice or P spice or something like that. KiCad could actually do those simulations within the tool. Apparently, I have not done that, but that's why power is under a separate menu. So I clicked add power, and I just want ground. So G and D for ground. Lay that in there. Okay. Start with a capacitor. Add in an unpolarized capacitor. Hit the R button there to rotate it. It's possible to edit your there's some settings menus somewhere where you can, and maybe it's under preferences, preferences. You can do things somewhere over here. Now that I'm trying to do this live, I'm guaranteed not to be able to find it. But somewhere under here is an option where you can change the number of degrees that your component will rotate by whenever you hit the R button. So you can change it so it will rotate by 45 degrees, or at least in the PCB view, you can rotate by 45 degrees rather than 90 degrees. But in schematic, that doesn't make any sense. You should stick it at 90 degrees. So one of the major improvements that's happened with KiCad in the last year is they have received substantial financial support from a number of companies and non-profits, I guess. So they have a professional staff of developers working on this, rather than just volunteers, professionals who are volunteering their time. They're professionals who are paid for their time to do the KiCad development. So the pace of development has accelerated. And in particular, they've had a team of people who have been really working on the built-in symbol library, the schematic, all the different components that are supported out of the box by KiCad. You don't have to import. You don't have to import a bunch of third-party libraries. Yes, Wade, you had a question.
Yeah, I might have to run this down later, but for some reason my symbol library is actually empty.
I have never had that.
So
Okay, yeah, it wants me to import it.
on the Windows download, I just did it as well. The first time you open it up, it's going to update libraries. So that he didn't show that, but that's going to happen for anybody who's trying to follow along on Windows.
Yeah, on Linux it didn't offer me that. It just wants me to import one, but I'll figure it out later.
Yeah, sorry. It's been such a long time since I installed KiCad that I don't remember that I did anything special. It should all be built in out of the box, but sorry, I don't recall.
Yeah, I'm guessing it's a problem with Arch Linux's distro of it. So.
Yeah, probably. Okay, so the point of all that is that I've actually had a lot of success, even for newer components, if I don't have to draw the symbols for the component myself. Or most of the time, when I try and place a component, the symbol will already be built into the library. So the next component to add is that that RF amplifier at the input to the device, which is I'll just open up my browser so you can see it. It is pick this this amplifier by Mini Circuits, the S66 Plus, for the simple reason that it's got a decent amount of gain, a nice low noise figure, covers our frequency range, and the most importantly, it has a surface mount by hand friendly package. It's the SOT89 package. This little, it might look small and intimidating, but this little package is fairly easy to solder as surface mount ICs go. So that's why we picked this one. This is a change from the T41 schematic. The T41 has a different amplifier, but it's a much smaller pin spacing that is harder to solder if this is your first time doing surface mount assembly, soldering by hand. So you switch the amplifier out for this one, which should work just as well. So need to place this S66 Plus. Now, I was very pleasantly surprised to find that when I was drawing up the reference schematic for this, that if I just search for S66, this amplifier is included in the KiCad library. I didn't have to do any of the drawing or any of the specifications. It's there. So this amplifier is, notice there's no power connector in there. We need to supply power to this amplifier by DC biasing its output. The data sheet for this amplifier, if you scroll down, has recommended application circuit, kind of how you should design your circuit very helpfully. If you run the math on this, this thing draws 16 milliamps in current. You basically want to end up with 4 volts at the output of the amplifier when it is drawing 16 milliamps of current. So in our case, we'll have a 5 volt supply on the board. So if you work out all the sums, we basically need that R bias needs to be 62 ohms. So I'll add the resistor, R for resistor, put that in. I'm going to put the value for this resistor in at this point. You could wait until the end to put all your values in, but I like to put them in as I go just so I can keep track. You could double click on the component. This window comes up, which is a symbol properties window. And then you can edit here under the value R. I could replace that with 62 R for 62 ohms. It's one way of doing it. You could, a different way of doing it is you could just click directly on the value there, double click on, in this case, I've already typed it in 62R. If I double click on that, an edit value field window will pop up and I could directly change the value of it that way. There's also the option, if you want to, you can hit view and you can show the properties manager, and it will open a pane off to the side that if you click on the resistor, that value field will pop up and you can edit it on the side if you want. So there's many different ways of doing this. I like having as much real estate as possible for the schematic, so I usually don't have this properties window open on the side. I like to be able to see more of the schematic. Yes, Mike. You're muted.
Indeed, this is Rick. I have a question. I can't seem to get the hand to go up.
Hang on, Rick. Mike, you're muted. You're muted still.
Oh, sorry. Mine came up with just 62 and it says text. Yours says 62R. Have I entered a value or a label? I'm not sure. I double clicked on it. I'm not sure what the difference was. You entered a R, 62R.
Yeah, I just like to put the units in there. I could just put 62 in if I wanted to, and that would be just as valid. I just, as a matter of as convention, if there's 62R, if it's 62 ohms, 62K, if it's 62 kilo ohms, that's just my personal preference when I'm labeling schematics. So there's no ambiguity about the units. Yeah.
Okay, who had the other question?
This is Rick.
Yeah, go ahead, Rick.
So I had this trouble when I try to use KiCad earlier. I double click on the component, left click, and it pulls up the choose symbol box again. It doesn't give me the properties for the component.
Yeah, I just did that. Hit the escape key first and then do it.
Oh, got it. Thanks. Thanks, team.
Okay.
Well, I'm glad you're here, Dean. You're catching all these questions.
Well,
I was like,
because I'm doing it while you're doing it, Oliver, and I rather than ask the question, I tried to figure it out.
all right. Okay, so now next component is an inductor. I just hit L there, and because I know that that's the shortcut to get to the inductor. In this case, hit the E button to bring up the edit window. I know we're expecting 1.5 microhenries. You know, we'll need some decoupling capacitors here to give us a more stable current, more stable voltage here at the output of the amplifier. Yes, Rich.
Yeah. So when you're choosing the components here, like resistors and inductors, where do you decide on the schematic of, is this going to be a surface mount resistor inductor, or is it going to be like the old school? I can't remember what it's called.
Yeah. Through holes, yeah.
Through hole, yeah.
Yeah. So you have a choice. You could decide it now. Like if I go to this resistor and I double click on it, or hit the E shortcut to bring up the edit window, I could decide here. There's this footprint field.
Okay.
I could at this point hit the little library, open the library button, and then pick the footprint. I know I want a resistor. Oops, can't spell. Resistor, and there's all the possible resistor footprints open up, and I could assign whatever footprint I wanted, at this point. That's one way of doing it. And if you're doing a simple schematic, that might be the way you want to do it. The way I'm going to show you is that, towards the end or at the end, once you've got all your components laid out, there's a different interface. I'll just give you a quick preview of it now. If you go to Tools, Assign Footprints, then a footprint assignment tool comes up, and that kind of is a tool that makes it easier to assign the same footprint to many different components at the same time.
Oh, okay. Thank you.
Yep.
Yeah, it clears it up.
So this capacitor, I hadn't put the value in. So another shortcut to use is, rather than hitting place, add symbol, type in C, find capacitor, and double click. That's like 5 different actions to pick another capacitor. A quicker way to do it, if now I need to place a couple more capacitors on the circuit, you click on it. You click on the existing component, in this case a capacitor, and I want to duplicate it. So if I hit Control D, I just duplicate the capacitor, and that saves a significant amount of time. Hit R for rotate, and now I've placed another capacitor. Control D, duplicate it again because I need 2 capacitors at this point. Put it over here so it's neater, and that was significantly quicker than going through that whole place, add symbols. Just a little shortcut to make life a bit easier. This one is in fact a 10 microfarad capacitor. Okay. Same goes for ground. These two. Make that power symbol first. So I now need a plus 5 volt power rail. So need 5. I will be supplying this LNA with 5 volts, and I'll need a ground. Duplicate that ground, put it over here to ground that output. Duplicate again, put it on each of these decoupling capacitors. So now I want to draw some wires to connect this all together to start actually wiring up the schematic. I could go over here to the right. This is kind of like your tool selector, if you will. It may appear somewhere different on your KiCad, but I think it appears on the right. You can add wire, or you could hit W, and that starts drawing a wire. Or you can just click on the unwired port, and it will move the mouse over the unwired port, and it will automatically assume that you're trying to start a wire. So you just click to start a wire. You can move it wherever you want, but move it to where you're trying to go and click to end. So I'm just going to wire up all of these, and across there, and there we go. So that's the input stage of the capacitor of the software-defined receiver. I'm just missing one component here, which is the decoupling capacitor on the output, because we don't want the DC bias that we're applying to this low noise amplifier to affect any downstream components. So that's this capacitor kind of like decouples that. So that's done the first stage of this. I just, as a personal preference style, I like to document my schematics with as much text and explanation and schematic art as I can, to try, not to make it necessarily look pretty, but to make it understandable. When I see a schematic, it takes me a while to figure out what all the bits do, and I find it very helpful if I'm trying to, learn or help other people understand something that I've drawn, just to add a little bit of schematic art to kind of point out the major components of a system, so it's easier for people to kind of figure out what a schematic does the first time they see it. So KiCad will let you add labels and text to a schematic. So I can I can add some text. Let's call this the input RF amplifier. I can make it bolded. I can change its size. I can pick the color. I pick a nice bright blue. All the usual text editing things. Hit OK, and now I can place the text on the schematic, and now I will add a add a rectangle to kind of draw around this input stage, so it's clearly delineated what is what. So that doesn't affect your ability to actually make an electrical device work. It just makes whatever you draw a little bit more comprehensible to yourself in the future and others who might follow along behind you. Right. So a very important thing to do, particularly if you are doing surface mount soldering, surface mount assembly, is to add test points, as many test points and test pads as you can to your schematic as you go, or circuit as you build it, because it is, if you imagine trying to poke little like a multimeter probe down onto a tiny little pad on the side of a surface mount capacitor, that's very painful to do. What you would ideally do is put little test points at all these various places on your board where you might want to examine the signal, such that you could put an oscilloscope probe attached to that and have it hook on and have your hands free. So I'll do that now. I'll add some test points. So place, add symbol, and I'm going to search for test point. Test point. So bunch of different test point symbols come up. These are just different art styles. You can pick whichever one you like the most. I like this triangle one today, so I'll use this triangle one. We'll want a test point here on the input, so we can examine the input RF. A mistake that I made on the first iteration of the T41 boards is I put a lot of test points on, but I didn't put the corresponding test point for the ground lead of the oscilloscope to connect to. And so I got to the point where I'm trying to test this board, and I can attach the the signal probe, but I've got nowhere to clip the ground lead, and I'm desperately trying to find somewhere on the board that I know to be grounded, maybe in the body of a transistor, so I can clip the ground lead on. And so I try not to delete that value. It doesn't matter. I resolved not to make that mistake again. So whenever I place a test point, I make a point of always adding another test point on the schematic right next to it that's just connected to ground, so that when I lay out the board, I'll be able to figure out which test point is which and make sure that I have enough ground points close enough to every test point that when it comes to debug and test the circuit later, I can do that. Okay. Okay, so doing a lot of talking here, and I don't think I know that in the time we have, kind of an hour, I won't finish the entire schematic, draw the entire schematic in this hour, given the pace at which we're going. What I'm trying to do is cover all the important points. At this point out, it becomes kind of pro forma and rote and repetitive. I'll get as far as we can. I'll cover some of the more important parts. But what I'm going to do when this is tomorrow is I will put the reference schematic that I drew, that I shared. I'll put that on a GitHub web page and send out the link to everybody. So if you want to download the KiCad schematic that I drew before and that we're trying to recreate here, you can download that and use that if you want, just to examine it or edit it as you see fit. But I'm not trying to race through and make sure we get the entire schematic finished tonight. What's more important is like the workflow and how KiCad works, because I've already drawn the schematic before. It's already complete. So the next section of this device is the mixer. So we use this 7.4 CBT LB, just flows off the tongue. 3253. Where do we have it here? We don't have. Here we go. 3253. Basically, it's a multiplexer switch that's like the heart of the Talo mixer. You'll notice here is you won't find that in your libraries, because KiCad does not have a symbol for this particular component in the library. You'll notice it popped up for me because I had previously drawn it for the T41 project. So I have a separate T41 library that has all the specific symbols that I drew for that project. So we're now at the point where we have to draw a symbol for a component because it doesn't exist in KiCad's built-in library. So how do we do that? So up here on the top is this box called the symbol editor. It looks like a op-amp with a little red pen on it. If you click on that, the symbol editing window will open up. Okay. On the left here, it kind of shows the symbol library, or all the libraries that KiCad has. Almost all of these are built in. In here is one. This is the T41 library. That has all the components I drew for the T41 project. You can we want to create a new library for this project.
In progress.
So we don't want to be editing the built-in KiCad libraries and trying to add components to them. I think it might actually give you an error and say that they're read-only if you try to do that. So we need to make a new library to hold all the symbols we're going to draw for this project. So I said File, New Library. You have a choice when you can create a library. A global library is one that KiCad will automatically make available to every other project you do from here on out on this particular computer. So that's why the T41 library popped up there, because I made that a global library when I set it up. If you're there's pros and cons to doing a project-specific library whose files will only appear for that particular project as opposed to a global one. In this case, I'm just going to go for a project-specific one as opposed to a global one. But there's pros and cons to both ways. So I double-clicked on the project, and this popped up, and I get to pick what I'm going to call the library. So rather than call it new library, I'm going to call it Vienna Wireless Society SDR. It automatically gives it a .KiCad_SYM KiCad symbol extension. Don't have to edit that. Just give it a name, a VWS software-defined receiver. Hit save. So now in my list of libraries of symbols, the VWS SDR has appeared, and I can now do a new symbol in this library. So I hit that new symbol button, give it a name, and it's this mouthful 74CBTLV3253. Okay. I'm not going to change any of the edits. There it is. And now you could add your pins, give them names, give them numbers. So we might call this one, say, VCC, and it's pin number 16. Normally I would be looking at the schematic, the actual data sheet. Here is the data sheet for this particular component over here. I'll be looking at the data sheet. I'll be looking at the pin numbers and the pin names, and I would be trying to create my own symbol that appropriately maps the name of a pin and the number of the pin correctly. That's basically all your schematic has to have. I'm not going to hit an R to rotate. I'm not going to try and recreate that symbol now because it's even more. The only thing more tedious than watching someone draw a schematic is watching someone draw a symbol for a schematic. So instead, I'm going to cheat and just copy what I already did for the T41 library. So I opened the T41 library, I just hit copy and open up this library and hit paste. There we go. Now I have added to our library this particular symbol for the multiplexer chip that is the core of the Taylor mixer. Save that, hitting Control S to save. I can close the symbol editor. Now, when I go back to my schematic and I say place, add symbol, and I want to search for that same mouthful 74CBTLV7253, I now have an option. My VWS SDR library that we just created is there, and now the symbol is available to me. So, like I said, this happens. The need to do this happens less and less often these days with KiCad, as they're adding more and more symbols to the built-in library. The need to draw your own symbols or import symbols from someone else's library has become less and less. There are many websites out there that will have KiCad symbols for you, that you can download the KiCad symbols for them. SnapEDA is one of them. You can create an account on SnapEDA, and you can download a lot of these, the footprints and the symbol assignment, the symbols and all that for components there. So you don't have to draw them yourselves. I just wanted to give you a quick view of how you would do that if you needed to, because for simple components, it's often quicker just to draw it yourself than it is to try and find an existing symbol that someone else has drawn somewhere on the internet and then test it to make sure, check it to make sure it's actually correct. So this is wired up like this. I need a resistor divider bridge here because I need to raise the DC level of this. I needed a 510 ohms, so this is 510R. There's my resistor divider bridge. This one is grounded. The wire symbol. Okay, and then this other end is we need a 3.3 volts is what we're powering this from. So I need a new power rail, add power, so type in 3V3. There we go, plus 3.3 volts, 3.3 volt power rail. And looking at my schematic, that also, I'm not going to click that up directly because I'm missing the inductor. Okay, I need a capacitor, a 0.1 microfarad capacitor over here to a little bit of filtering on that. And I'm going to add a little RF choke here. This is a ferrite bead. There's a particular component that acts as a little RF choke to filter out, stop any RF or any high frequency noise generated by this mixer from leaking back out onto the power rail. Keep the rest of the circuit clean. Duplicate that capacitor. There's going to be a decoupling capacitor over here. Make that up like that. And then add a ground on that side. So that's, we now powered up this mixer. We're biasing up the input level appropriately. These output enable lines need to be pulled low because they're enabled low. So let's add a just do a 10K resistor to ground to pull those both to ground so that outputs are enabled. And these two over here, S0 and S1, these are our clock symbol. These are what we drive with the quadrature clock. So rather than have lines running off to somewhere else where I'm going to draw the quadrature clock, I'm going to introduce you another concept here, which is labeling. Excuse me, labeling lines. Makes it a little bit easier, a little bit less tedious to makes your schematic less clustered. You don't have to have lines running all over a complicated board. So if you say place, and I'm going to add a label, add label, or I could just hit the L button. I'm going to give a name to this particular net, to this particular line in the schematic, and then every time I use that name, KiCad knows that they're all connected together electrically. So when you do the PCB layout, it knows to draw lines to them all and say, hey, you actually need to draw a conductor that connects all these points together. So we're going to call one of them clock 1. That one over there is going to be clock 1. And duplicate that, make that a little bit easier. And move it so, I'm going to zoom in here so you can see. I'm moving it so that this light brown box kind of coincides with the pin point, and now it connects them electrically. So when I now move this text, it will automatically fill in the green line. Just saves a little bit of clicking, a little bit of switching to the wire tool. Now I'm going to rename this one. This is going to be 0. Double clicked. Now it's clock 0. So now when I add the SI5351, I just have to name its outputs clock 0 and clock 1, and then they will automatically be connected kind of like, electrically to these 2 points on the schematic. So let's do that. So I could, at this point, for the SI5351, to add symbol, do SI5351. This is the component that generates the clocks to drive the mixer, the digital clocks. I could add the SI5351, wire it up. But what we're actually going to do with this project, because this component has a very fine leg pitch spacing of its legs, it's very hard to solder. surface mount assembly style, particularly if you're doing it by hand with a soldering iron. I have never successfully soldered it flawlessly the first time. I've always had a solder bridge and I've had to rework it. So just to make everybody's lives a bit easier, rather than doing the surface mount assembly of this ourselves by hand, what we're going to do is we're going to use one of these breakout boards, which you may have worked with in the past. Adafruit makes one where they will sell you this board where the SI5351 is pre-soldered, and they've added all of its necessary. They've added its crystal oscillator that it needs. They've added a little bit of like logic level shifting and pull-up resistors for the I2C lines. So this is very convenient. It's a nice, convenient form factor, pre-soldered. We can just do some much easier, through-hole soldering for getting this component. So I don't have to add that SI5351 to my schematic. Instead, what I want to add is a 7-pin, just a 7-pin header connector that we can put a little 7-pin header on 2.54 millimeter spacing, put it on our board, and then just solder this one in on top with just a standard pin header. So I'll do that now. Deleted that component. Place, add symbol. And I know from having done this before that the magic words to type are con_01x07, and that will get me to the generic connectors, or pin socket. In this case, we want a pin connector 0107 pin. That's just a generic connector for a line of header pins. Double click on that, and I can add this into my schematic. Now, if I take my clock 0, that one's clock 0. I'm hitting hit Control D there to duplicate. Click on something, hit Control D to duplicate it. Just makes life a bit easier than having to retype things and rename things. We aren't actually going to use clock 2 in this project, but I'll just add a label to it just so it doesn't feel left out. We go back to the Adafruit board. That's clock 0, clock 1, clock 2. Then we've got the SCL and the SDA lines for the I2C. So this is SC edit. Hit E for edit, SCL. Zoom in some more so you can see what I'm doing. SDA. I clicked on one, hit Control, clicked on the other, so I've selected them both, and then just drag to the right, so that you can clearly see that pin's connected. That I've got the green line. There's no ambiguity in my mind about whether that was connected or not. And then finally, we've got ground and V in. So we need a ground, one of our ground. One's over there. And we need V in. We can power this thing from 3.3 volts. So where's our 3.3 volt? There's our 3.3 volt power connector. Duplicated that. Come down here and just connect that up. Come on. Here we go. So now our clock is there for driving the SI5351. Okay, so rather than continue to draw the rest of the schematic manually, given that we're getting near the top of the hour, I think I've shown you all the major parts of what you do at this stage. So we would continue doing this, finding components, placing them on the board, and if they were missing, drawing them ourselves or downloading a library from somewhere on the internet. I'm going to show you one more component, because it's a slight variation of what we've seen before, and then I'll show you some of the bulk editing tools that we talked about earlier, and then we'll be at the end, and maybe we'll just talk through the final schematic, point out some of its features, and then we'll wrap up. So, final component I want to add here is op amps. So these, the output of the SI5351, SI5351 drives the mixer. The output of the mixer goes into some differencing or some summing, some op amps. So the T41 radio used the MC33078 op amp. There are alternatives to this op amp that you could use, and we'll talk about that in a second. But what's crucial about this one is this particular package in a particular 8-pin SOIC integrated circuit, there are 2 op amps in it, and that KiCad knows that. So if I select this one and I click, you'll notice that I'm pointing with my finger, which you can't see, but you'll notice it says U3A, which indicates it is the first of the 2 op amps that I'm placing here. So if I click, it places that, and now I've got the option to place U3B, which is the second of the op amps that's inside this particular IC chip. So it will place that, and finally it will come up with this, which is C, which is basically the power rails for the op amp. So rather than having a single symbol that had, click this, so I'm not pointing with my fingers anymore, that had this op amp drawn in it and this op amp art drawn in it and had these power rails drawn in it, the way that KiCad does it is they're kind of essentially placed as like 3 separate components, but like one after the other, and KiCad automatically moves you on from one to the other. So I just wanted to show that to you in case it was not obvious. So, let's assume we've finished out the whole board and we're now at the point that we need to assign footprints to everything. So the way to do that quickly in a kind of a bulk method is, I hinted at it earlier, is you do tools and assign footprints. There's several ways you can do it. This is the most obvious way. Tools, assign footprints, and this window comes up. What I like to do when I'm doing this is I just double clicked on the header bar to make it not full screen. There's this one over here. This is view selected footprint. If you hit this button, a footprint viewer will open up. Let me put that off to the side. Now, if you click on a component here in the right-hand column of the assign footprints button of a particular footprint, you can now see what that looks like in this footprint viewer on the left, which I find just helpful as a sanity check as I'm going to make sure I'm doing the right thing. So let's get started with these capacitors. So also see, if I had a big enough screen, is as I click the different capacitors, they get highlighted on the schematic. So it's helpful to figure out exactly which component you're talking about. So as you move around, as I click on them, KiCad will automatically recenter the schematic window on the component that I've selected, which is a very helpful thing. The screen is kind of small and it's hard to see, but if you've got a big monitor and you can have multiple windows open side by side, that's very helpful as you're doing this editing to know which component it is that you're editing. In this case, it's very simple. I know these are all surface mount components, so I can click on the first one, hold down the Shift key, click on the last of these capacitors. So now I've selected C1 through C6. So whatever footprint I pick here on the right will be assigned all 6 of those at once. So on the left here are the different footprint libraries. These are capacitors. This is the capacitor SMD library, surface mount device library. These were, if I wanted to use a through-hole footprint, I'd use capacitor THT. It's all the through-hole ones. But these are capacitor SMDs. And I know we're going to use size 1206, which are imperial size 1206, which is metric size 3260. Which one of the confusing things about surface mount components is there's like an imperial size designator and a metric size designator, and sometimes they are the same. They share the same designator, but they're drastically different sizes. So you'll see here's a 1206. This one here is a 1206 imperial size. There is also maybe it's 0805 is there's an 0805 imperial size, but there's also somewhere here an 0805 metric size. That's a very different physical size. So that's just a gotcha that will catch you at some point working with surface mount devices. KiCad makes it unambiguous by giving you both the imperial and the metric in the footprint name, just to make it harder for you to make the mistake. So capacitor, surface mount, imperial size 1206, which is 3216 in the metric size scale. So that popped up over here on the left. They're very helpfully put in the name. It's 1.33 by 1.8 millimeters in size. This is the hand solder version. If I pick the other one that it has the same size designator, you look at the difference between them. Oh, that's not very helpful. Changes the zoom level. Maybe that's easier. Yeah. Yeah, that's not very helpful. If you look very closely, you can see the hand solder version has a slightly extended pad. If you're trying to get a soldering iron in there, get some solder in, it's a little bit easier if you're doing hand soldering to use the hand solder version of the footprint. So that's what I'm going to use. So double click. Once I've selected the one that I want, double click will then apply that to all the components that I have selected here in the middle. So if I double click, that's what happens. So now I've assigned this footprint to all 6 of those. And if I hit the apply, save schematic, and continue, hit OK. Now if I open up one of these capacitors by double clicking on it, you can see it's now filled out the footprint for that particular component. I didn't have to go through and edit each one individually. I was able to do it in bulk for all of them. So we go back to the assigned footprints. We can see that very helpfully for us, they already have KiCad. People who made the KiCad library have already assigned a footprint for the LNA. We don't have to pick the footprint for that, which is helpful. These 2 inductors and these 4 resistors, those will all be, we'll just use the resistor, where is it? Resistor surface mount device 1206 size for those as well, with the hand solder variant. Now we have assigned footprints to all of those. This is a coaxial SMA connector. If you can scroll around and search, there is also the option to filter. And I believe if I type SMA in here, oh no, that's unfortunate. It's over here. Was that the viewer? There was a shortcut I thought to make that a little bit easier, but I can't recall what it is. I guess we have to do it the hard way. We just need to find RF, not under there, somewhere here, and I don't remember exactly where it is. Maybe it's under connectors. There we go. Connectors, coaxial, SMA, and there's a bunch of different, open up the footprint viewer again so we can see what we're talking about here. There's a bunch of different footprint styles for various SMA connectors. They come in different footprint sizes. This is kind of a tricky one that's caught me in the past. Yes, Rick?
Oh, I think I figured out. I got lost as to which tool we were on. Footprint editor.
Yep.
Thanks.
Okay. If I'm here in the footprint viewer, just move it to the front. You can use the measure tool over here on the left. Click in the center. If you're trying to get, if you have, for instance, I had an SMA connector here on my desk, and I want to get the one where the little legs, the ground legs, are 5 millimeters apart. Make sure I've got the right footprint. You can actually get the physical dimensions of this footprint and do a little sanity check yourself before you pick it. So I think this is the right one. So I'm going to pick this one and apply it. Now this is the DIN, the 2.5, the pin header connector, pin header 2.54 millimeters, and I want the one that is yeah, that looks about right. 7, 1 by 7, 1 by 7, have a sound that footprint. So you can continue and so forth and so forth and so forth doing that, assigning footprints to all the components. Okay. One more thing I'm going to show you now before we kind of wrap it up. Sorry, you've gone slightly long here. Is one thing that I like to do, because I want the I like the KiCad model to be as complete a compendium of the project as possible. So I've got fewer sources of information. Is I like to put the bill of materials part number into the schematic. So if there is a particular 0.1 microfarad capacitor on Mouser or DigiKey that I want to use, I like to add that to the schematic so that I've got it in one place, and then KiCad has the ability to generate a bill of materials, so you can generate a kind of file that you can then just upload to Mouser or DigiKey and place a bulk order. You don't have to have spreadsheets that you're trying to keep track of separate from your schematic. If you put all that information into your schematic, it makes that buying all the parts easier down the road. So this is an opportunity to show you the last thing I wanted to show you on the schematic editing, which is if I go to Tools and I go to Edit Symbol Fields, you can do like a bulk edit of all the symbols in your library. So I can add a new field that will then be added to every single one of the symbols. So in this case, I'm going to add a new field here by hitting this plus button, and I'm going to call it Mouser PN, or the Mouser part number. If I do that now, just so apply safe schematic and continue. Now, if I open any component, it now has a new field added to it, which is the Mouser part number. And I can go in and add the part numbers for everyone, or use the same edit symbol fields, because it kind of groups components together by value and by footprint. So it's grouped C1, C2, C4, and C6, 4, 5, and 6 together because they all have the same value and all have the same footprint. So I can apply, just make this a little, take this so I can see it, make this a little bit bigger. I can now apply A, B, C, D, 1, 2, 3, the same part number to all of those components in one bulk step. I don't have to go and edit each one individually. So this is how I like to track the part selection for a particular component. It's all there in the schematic. I generate the bill of materials from the schematic. There's just one authoritative source of truth for the design, which is the schematic itself, and everything else is derived from that. Okay. So I just made that, I made up that part number, and now it's been applied to that part and to that part, but not to this part because it has a different value. So it wasn't selected, it wasn't grouped with the others. So that's another way of making this workflow a little bit easier. So you would continue in that vein, and eventually you would end up with, I'm just going to save this. I'm going to change projects to the reference schematic that I drew back in December to see if we continue doing this all evening, where would we end up? Just closing the schematic editor. The project view is still open. I'm going to open open project, and here's the reference design, the project. If we continued in that vein, doing the rest of the schematic, we would end up with this. So we would have drawn everything for all of these. Edit. I've already picked out the mouse part numbers. They're all in there. Filled out the rest of the schematic. We talked about for these op amps. Several people brought this up. I think Lee was one of them. Maybe Mark was another. One of the Marks suggested alternatives to the MC33078, and I found a few alternatives that have exactly the same footprint, so you don't have to redesign your schematic. You don't have to redesign your PCB. They've got the same footprint. They've got the same pin assignments and the same voltages. So we can try several different op amps without having to change the design at all, because they have the same footprint and the same pin assignment. So you could, as an alternative to, in this stage, you could use this 8599, or perhaps the OPA 2209. There's a couple of different op amps that got slightly better performance, lower noise figure, lower added noise than the MC33078. So, I did a few other tricks on the schematic. One thing I like to do is, if you need board mounting holes, like there's some certain physical features we will want on our PCB at the end of the day. I like to add them to the schematic so that I'm doing less drawing of special features like board cutouts on the PCB. So I add board mounting holes to my schematic, and then it will automatically give me a hole to place somewhere on the board. That makes it easy if I want to change, like rather than having a 3mm diameter hole, I want a 2.5mm diameter hole. I can just change the footprint assigned to that assigned to that particular hole, and then we'll update the PCB appropriately. I think that was the gist of it. Yes, Rick.
Yeah, so that was a lot. Thanks. I got a question about the end. If we can substitute in different amps in the board, is it feasible to actually model this with the internal spice in KiCad, NG spice? Can you actually do that, or is it just too complicated a circuit for that to work?
I believe it is feasible. I'll have the caveat that I have not tried to do that. There is a feature of KiCad that I have not explored yet, is trying to do that spice modeling within the tool. So I believe it to be possible, but that's based on belief, not experience.
Yeah. Thanks.
Sure. You notice another thing I've added to this, the kind of lesson learned and gained through bitter experience. You see all the test points that I mentioned. Every test point has a corresponding ground test point next to it, so I have enough grounds to clip oscilloscope leads onto. We're going to use the Pico microcontroller to do the translation. Serial commands over USB from the computer getting turned into I2C commands to the SI5351 clock generator. This microcontroller has a bunch of other GPIO pins on it that we aren't going to be used. So rather than leave them inaccessible, I've added some breakout headers, just some extra pins. They'll just be holes in the PCB that if someone wants to experiment with their board and they want to flash an LED, or they want to route more signals in and kind of use the same piece of hardware to do more things, I've made those pins accessible so you can get to them more easily without having to modify the PCB. Also, you see over here the I and the Q outputs from the IF chain that would connect via this audio connector to the sound card. I've also added a little 3-pin connector that, if you wanted to, you could add kind of off-board wires to connect them to the ADC inputs of the Pico, because there are some projects out there where all that demodulation that we are going to do in a computer use the sound card to digitize. The demodulation will happen in a computer in Quisk. There are some projects where people have implemented all that digital signal processing on the Pico itself, so you could actually do the full demodulation, turning into audio on the Pico if you wanted to. So just if people want to do experiments like that, let's make this board a little bit more capable. Yes, Mike.
Yeah, I got behind. No surprise, trying to do this while listening to you. How do the clock and I2C bus connectors get connected together? Did we designate those pins somehow?
Yes. So you'll see.
I figured I missed that. Yeah.
Yeah. So that's what these little text labels are here.
Right.
If you hit place and you say add label, you might have seen these called ports in other CAD tools. I just use the label feature in KiCad. Add label, and then you can give a name to a particular net within the schematic.
Okay, so when it sees a label, it automatically connects those.
Yeah, so it knows that this clock 0 here is the same as that one there, and those are automatically connected together. I don't have to physically draw a wire going across the schematic. It helps keep things a bit neater.
Yes, thank you.
And similarly, there's SDA and SCL for the I2C.
Bus, yeah. Okay, thank you very much.
You're welcome. And then the other feature is, we'll be supplying power to everything from the USB. So we just added some circuitry over here based on this data sheet, this guide on the internet of how to clean up USB derived power to get less noise in your analog circuitry. Yes, Mike, and someone else. Who else? Mike and Rick. Okay, Rick, you raised your hand.
Yeah. So just looking at this, and how complicated would it be to swap in ESP32 for the Raspberry Pi?
Not hard. So I'll do it live. Place, add symbol. Reasonably confident that there we go. There are a lot of ESP models built into KiCad because it's so popular. They've actually put all these ESP variants in there. So I just searched for ESP, and here are a whole bunch of different ESP variants. And so find the one that works for you.
Yes, but the programming is one thing, but in terms of when you do the rest of KiCad for board layout, is there going to be a lot of changes other than designating which pin in ESP32 you connect to?
Yes, there will be, because they have different footprints. So there'll be a lot of routing changes that you'll need to do when we get to that next time with actually doing the routing of the board. That'll be quite different. So you kind of don't want to, you want to make the decision now when you're at the schematic level of which microcontroller you're going to use, so you aren't having to reroute a microcontroller at the end of the day, because that will be very tedious. Possible, but tedious. So,
and again, one of the philosophies or one of the goals of this project is not to kind of do everything, right? So Oliver's kind of made some basic component selections for the purpose of this project. That's what we're going to go with, but you have the option of doing whatever you want kind of on your own. But in order to keep this bounded so that we can actually finish, we're going to kind of stick with the core component selections that Oliver has chosen.
Mm-hmm. Yeah, and the ESP32 would work just as well for this. There's nothing magic about the Pico. I just picked it because it's similarly low price, $4 a board, and I have a whole bunch. I happen to have a whole bunch, and I happen to have been doing a bunch of Pico programming recently, so it's just convenient. So the next stage after doing this is when we would do the physical layout of the board. We won't do that now. We will do that in 2 weeks. So I can hang around a little bit longer if anybody else has any more questions. But basically, that's what I was hoping to get through this evening. Is kind of like that workflow of how you physically lay things out. Just a few little tips and tricks of things to look out for. Some of it is specific to surface mount soldering, like make sure you've got enough test points and pick the right footprints, and be careful of the metric imperial ambiguity at times. But a lot of this is just generic if you're just doing no matter what it is, your whatever surface mount through hole, you would use this same whip flip. There's nothing with whip flip. There's nothing special about that particular tonight. The last thing to point out here is there is this title block in the bottom right corner. If you double click on it anywhere in there, double click on some text anywhere in there, this comes up, and you can add some details like the issue date. You can revision numbers, titles, all that kind of stuff. That's how all that text in the bottom right corner is filled out. And tomorrow I will take this schematic that I've drawn here, and I will put it on GitHub and email everyone a link to the GitHub page. So if you want to work from this or edit this or just see what I've done, you can take advantage and not just have the PDF.
And for Q&A, let's use the VWS Maker email reflector on all of this to kind of keep the conversation in one place. So I think with that, I want to say thank you, Oliver, and I want to kind of wrap up the kind of recording session of this. This was fantastic. I stopped trying to copy after we got through the input amplifier, and I just started watching because I wanted to kind of absorb as much as I could. Plus, we didn't have the IC that we needed anyway in the library, but seeing how to kind of build your symbol is really, really important. So again, thanks very much. Everybody, if you want to hang around, if Oliver's want to hang around, we can do Q&A and chit chat as long as you want. But with that, I'm going to wrap up the meeting and just say thanks and 73 to everybody.